Hello, and welcome to CFD Research Corporation's Tech Talk on our current Phase 2 SBIR project, titled Reduced Order Modeling of Unstart in Liquid Fuel Scramjets. I'd like to start with a brief overview of our company. CFD Research Corporation is an employee-owned small business headquartered in Huntsville, Alabama, with offices in Dayton, Ohio, and Fort Walton, Florida, and experimental test facilities in Hollywood, Alabama. We currently have over 330 employees, approximately 60% of whom hold advanced degrees. Our core capabilities span modeling and simulation, software development, hardware design and prototyping, and test and evaluation. CFD Research has transitioned several technologies to market, and we have spun out 6 companies to date. We hold 80 patents, with 40 actively licensed. Our company has also successfully transitioned battery, weather modeling, machine learning, and design optimization software through the SBIR program, with each of these technologies supporting DoD programs under Phase 3 SBIRs. Our DoD SBIR Commercialization Achievement Index puts us in the top 10% of companies nationwide. Next, I will motivate the present SBIR effort with a high-level overview of the technical challenge we intend to solve. Hypersonic air-breathing engines, such as scramjets, are prone to unstart events, wherein the internal flow becomes choked. This causes an immediate loss of performance and maneuverability, posing a substantial risk to future hypersonic vehicles and weapon systems. Detailed simulations and experimental test campaigns can probe the boundaries of the flight envelope, but their use in mitigating unstart is severely limited by cost and turnaround time. The Navy thus requires a tool capable of rapidly predicting unstart events for candidate vehicle designs across different flight regimes. It must account for the relevant physical mechanisms as identified by detailed simulations, including configurations utilizing typical liquid aviation fuels. Such a tool would have immediate applicability to any air-breathing hypersonic weapon program, such as the Air Force Hypersonic Attack Cruise Missile and Project Mayhem. Designing future hypersonic naval weapon systems requires fast evaluations of candidate designs. However, current approaches rely on low-order models of the propulsion system, which are not sufficient to predict unstart. To address this need, we are developing a tool which accurately predicts unstart and other performance metrics in scramjet engines, reducing the schedule and dollar costs associated with testing physical hardware and running detailed simulations within a design cycle. The tool additionally enables virtual testing of techniques for preventing and recovering from unstart events, such as feedback control algorithms for hardware-in-the-loop simulations, reducing in-flight risks in turn. To achieve this capability, we are employing a 3-pronged approach. First, a set of high-fidelity CFD simulations of multiple scramjet experiments are underway to provide fundamental insights into unstart mechanisms, as well as a reference data set for verification and validation of the tool. These simulations are targeting configurations with gaseous fuel, such as the HiShot 2 pictured here, as well as liquid JP7 fuel. Second, the core tool is being developed into a generalized system-level scramjet modeling framework based around a GPU-accelerated quasi-1D reacting flow solver. The ability of this solver to capture unstart was demonstrated in the first phase of this project. Third, an API has been developed which couples the propulsion model to a DoD 6 degree of freedom trajectory simulation software to simulate in-flight operation. This API will be used to demonstrate closed-loop feedback control and investigate unstart detection and recovery. As of July 2025, 6 months into the 30-month Phase 2 base period, the scramjet modeling framework has been extensively updated. Several key physical models have been implemented to improve the accuracy, and the solver has been refactored into a modular architecture to support future developments and extensions. An interface between the scramjet model and the trajectory simulation software has been developed and demonstrated on simple test problems, with work underway to support feedback control and more complex scenarios. Detailed CFD simulations of the liquid JP7 scramjet experiment are in progress on DoD HPC systems, proceeding in parallel with other non-reacting cases. Preliminary comparisons between the CFD and model predictions show promise. A key discriminator of the scramjet model is its immediate applicability to a broad class of vehicle designs and fuels, owing to its flexible system-level framework and time-accurate physics-based approach to modeling the flow. The emphasis on reduced time to solution has led to a GPU-accelerated solver, which approaches and may exceed real-time simulation. Coupled with the interface to trajectory simulators, this is a major enabler for iterative design, risk mitigation, and mission planning applications. Our scramjet propulsion modeling framework is uniquely positioned to reduce risk for current and future hypersonic air-breathing weapon systems. We anticipate procuring additional research and development contracts to integrate this tool into established scramjet design and trajectory planning frameworks. We plan to offer engineering services to adapt and apply the modeling framework to specific use cases and new applications, such as solid-fuel ramjets. As the software matures, we plan to seek additional revenue streams through maintenance and support contracts, software licensing, and training. We are looking for advocates within the DoD to help transition this technology into relevant hypersonic programs such as MACH-TB, HACM, and Project Mayhem. We are also interested in connecting with prime contractors working in hypersonic vehicle design and mission planning who are interested in evaluating this tool for their use cases. We plan to release prototype versions for beta testing, using the feedback and insights into real use cases to help refine the tool's capabilities and user experience. We appreciate your interest in our reduced order modeling approach for rapid prediction and mitigation of Unstart in scramjets. If you would like to learn more about this technology or are interested in potential collaborations, please reach out to us directly via the provided emails. You may also learn more about our other hypersonic research capabilities on our website at cfd-research.com. Thank you for your time.